Hi, my name's Colin Gordon, and I'm going to talk to you today about some work I've been doing on making it possible to write property-based tests in natural language. Natural language specifications in general have been sort of a long-standing, ideal in software engineering in the sense of being something that we've always kind of thought, well, this would be awesome if we could make it work. Where we could, ideally just describe in natural language how we would expect the software to behave, and have this correspond to, some form where actually, we can directly compare the software to that natural language description of behavior at every level, from unit tests up through top-level specifications. And this is fundamentally hard for all sorts of reasons, among others, linguistic challenges, right? So natural language tends to have a decent amount of ambiguity. There are problems with open vocabulary, right? Every new domain, every new code base makes up terms or reassigns existing terms. There are computational problems just on the linguistic side, right? Because we have natural languages that are complex enough to require context sensitivity in their parsing. So I'm far from the first person to try to tackle this. So there's been a fair amount of work in the past on template-based techniques, which have limits, right? They make very strong assumptions on sentence structure and how many clauses you can have and the complexity of those clauses, which, can make these things, usable but still pretty awkward. So if we want to generalize past those kinds of templates, we have to throw machine learning at it, right? Well, maybe, but at least not in this talk. Because I think there are some pretty critical mismatches between at least current ML techniques and what we would really want out of a solution that lets us write any kind of specification, but especially tests in natural language. Current ML techniques, especially neural network techniques, are inherently non-modular. It's hard to extend them with new vocabulary. There's been some good work in the past few years on open vocabulary handling for these systems, but they are limited to statistical properties, right? There's no way to actually guarantee that something like a large language model is going to do the right thing with your new vocabulary. And so if it does make a mistake, it's impossible to actually correct the mistake, in the sense that, yes, you could add more training data and retrain, but if you want to just go in and fix just this one word that it's doing something wrong with, you can't, right? Because there's no one place to go fix that word, which is related to the fact that they're pretty opaque, right? We don't know, we can't say that much about the structure, right? So people are working hard on providing explanations for NLP techniques, but most of these techniques based on neural networks, they don't really describe why a neural network produced a certain output in the sense of a linguistic explanation of the network is treating this word like it means this. They're actually just saying this was the word that had the biggest impact on the output, which is not really, not necessarily actionable. So I actually turned in a different direction, and I'm going to talk about using some more classic linguistic ideas going back into the 80s. Linguists have spent decades building really rich formalisms for modeling compositional semantics. That is, how you take individual words' meanings and combine them based on the parse of a sentence to build sentence meaning. One broad umbrella of techniques in this space is called categorical grammars. And I happen to have worked with this one variant called combinatory categorical grammars, but that more specific version is not super important for this talk. The basic idea in categorical grammars are that you compose word meanings in lambda calculi with some kind of truth type, technically a Heyting algebra, but anything that looks like a Boolean and or not and so on will get you there, right? And this has been used extensively in linguistics research. So there are very thorough treatments of large corpora of words in, full texts in English, German, Dutch, French, Japanese, Hindi, and other natural languages, built by linguistics experts rather than something automatically constructed. And this includes coverage of things like context-sensitive grammatical phenomena, which are really important, right? So this is something that we know is strong enough to capture all of natural language in principle, and that has been extensively validated on large corpora of actual natural language in many natural languages. From a technical perspective, we end up with something that is basically a logic. So here's a rule that says basically if we have a sentence fragment whose grammatical role is x/y, which means if you put a sentence fragment with grammatical role y to its right, the result will be something of grammatical role x. And then, oh look, we put this sentence fragment delta with grammatical role y on its right. Well, then the result is an x. And moreover, if we have semantics for both of those pieces, the semantics of the combined sentence fragment is actually just function application, right? So these slash grammatical types, right, basically are saying this is a grammatical type that needs an argument of a certain kind. And so there are ways of saying, well, we look for an argument on the right, or we look for an argument on the left, because, of course, some grammatical constructions modify words that come before another word. And if you build these together, right, in the same way you would build a typing derivation or a logical derivation in a more typical logic, you can actually parse out things like 3 is even means that 3 mod 2 equals 0. And you might notice, of course, this is false, but that's actually kind of the point. We want to be able to claim things that are false so that we can write tests that might not pass. So what does this have to do with property-based testing? Well, so property-based tests they're a kind of parameterized unit test that uses guided random generation. So there are combinators to compose and filter randomized generators. And there are combinators to express the desired properties, where these combinators do things like say that this should be true and this should be true, or this should be true or this other thing should be true, and so on. And at the end of the day, these are really fundamentally expressing universally quantified logical claims. So most of these tests have roughly the shape of this form, right? The details might vary from language to language, but they end up being roughly for all generated inputs from some particular generator that you've constructed. Some property is true, where this property is a predicate that you basically, or rather I should say, the testing framework will check for every input that is generated by that random generator, up to a bound, right, of 100 or 1,000 or whatever number you see fit. So the truth of these things is randomly probed based on these randomly generated inputs, but the underlying claim is still a logical claim, which means we can use these as a truth type for categorical grammar, right? So what does that end up looking like, right? So as a slightly more verbose example, so here's what we'll call a lexicon entry for every, right? So this is basically a rule for what does one kind of use of every mean. And you don't have to parse all the details here. The short version is if you write every followed by, in this order, an adjective, then a common noun, and then basically a sentence fragment that's missing a subject, this turns into one of these for all claims that happens to filter the output of a generator based on some property. And if we put this together with a few other lexicon entries, we can actually generate, semantics for things like every even integer is odd. This parses to a sentence, and its generated semantics are for all generated integers filtered to be even, the predicate odd should hold. And of course, this is also a failing test. So I took this and I built enough of a lexicon, so enough characterizations of individual words, grammatical roles, and meanings, to tackle the examples from the property-based testing chapter of a draft textbook. I'm not going to name the textbook in the talk. It is in the paper because that part of that textbook has been totally rewritten. It's great. I did make mild adjustments to simplify the English slightly. Basically, I removed some parentheticals because those can be handled by categorical grammar, but the semantics, as I was writing this by hand, are a little hairy. So I opted to just slightly simplify the English. And that textbook chapter had 3 sentences specifying some properties related to auto-grading, and 4 specifying basically properties of the classic FizzBuzz problem. I put all this together in an existing categorical grammar parser that's built into NLTK, the Natural Language Toolkit in Python. And basically, it can parse these sentences into essentially an AST that you can transliterate into JavaScript after the fact. So overall, to handle the 29 words that occurred in these tests, I needed 46 lexicon entries. Some words are reused multiple ways. This is common, right? We have multiple grammatical rules for some words. Plus 3 of these were specific to the programs that were tested, right? So passing, in the case of the grading example, and of course FizzBuzz, if you want to talk about what the FizzBuzz function does, you need to have a word for FizzBuzz. Turns out 3 of the FizzBuzz tests were actually underspecified. So the translated tests are correct literal interpretations of the English that end up failing because they underspecify the domain. Basically, they don't. It's the same underlying cause in all 3. They don't rule out negative inputs. Now, this was likely intentional because this was a textbook, and we often make these kinds of simplifications for pedagogical purposes. This is part of the reason I don't want to complain about the textbook, because it really is actually a very nice book. But I think this is important because it looks a lot like when we do this unintentionally as well, right? So this is a case where it's easy to sort of forget to specify this thing that's sort of obvious in your head, but then if you forget to write it down, it's also easy to forget to write it in your test. If I clarified these and translate those results, then the result is actually a passing test. Briefly, we can look through some of these results. So in each of these rows, you can see the original text, and after a squiggly arrow, how I rewrote it. So I'm not hiding anything there. And then finally, basically a serialization of the AST that later got rewritten into JavaScript. These ASTs are a little bit more concise than the actual JavaScript that gets spit out. And as you can see, there's not a huge change here, right? And mostly, like I said, removing parentheticals. So that's useful. Okay, so we found some underspecification in a textbook that, again, I suspect was intentional, but is sort of emblematic of what happens when it's unintentional as well. I went a little further. I went digging around for other examples of property-based tests, and I didn't translate them, but I did dig up 19 more property-based tests from 3 other textbooks covering property-based testing. All of these can be parsed by existing grammar-only CCG parsers. So I grabbed an existing off-the-shelf CCG parser that only does grammatical parsing. It doesn't have semantics for words. Since they can be parsed by that, then it's feasible to extend the prototype to them. I did find that one book actually also specifies FizzBuzz and repeats the same underspecifications. So that also is again, there's this question of, was it intentional? Likely. Was it unintentional? It's at least similar to what we expect unintentional underspecification to look like. We also came away with some interesting grammatical findings. We found a grammatical novelty that is something that you don't actually need for standard English semantics, but for translating things into these property-based tests that have more nuanced computational meaning. We found that we actually needed to subcategorize common nouns. So if you think about translating every integer is an integer into a property-based test, the first occurrence of integer needs to be a generator. The second occurrence of integer needs to be a predicate, because we're doing this for JavaScript. And this is why our grammar splits common nouns into cn_gen for generator and cn_check for checking in order to distinguish these 2 kinds of cases. So some of you might have caught, as I was going through that earlier example with every even integer is odd, that I actually had this on the slide. That was because that use of integer was, in fact, a generator usage. So this is actually, it's necessary in order to do this, but it's not totally off the wall. So it turns out there's actually some classic linguistics work from years ago that studied mathematical text, where they ended up doing the same kind of categorization to talk about things like, well, this concept only applies if the thing you're talking about is an integer or a ring or some other thing. So this kind of sub-categorization directly in the grammar is not totally new, but this is new and specific to property-based testing. So as we continue working on this and scaling this up, I expect we'll probably find a few more of these. All right, so before we go, a couple more questions that people might like to have answers to. First, I haven't said too much about building the lexicon, right? This is the database of this word has this grammatical role and these semantics. Do we have to do this manually? In this work, I did it manually because I was working with a small enough set that I felt okay doing that, and I wanted to make sure things were working and build some more insight in the problem domain, which is part of how I came up with the checking versus generating common noun split. But do we have to do this? In principle, no. So linguists have studied lexicon inference for various flavors of categorical grammar. So those systems exist. They would need adaptation for any new grammatical types, but the core ideas should transfer over. In addition to that, like I said earlier, these have been heavily validated on existing corpora of natural language texts, at least for grammars, not necessarily for semantics. And so there are existing large databases of known grammatical types, right? So for English, there's this CCG bank. And there are similar structures for German, Hindi, and a number of other languages as well. And since most words are going to still have at least the same grammatical roles in standard English or German or Hindi or so on as in the technical setting where we're talking about tests, we can probably take and reuse those existing grammatical types as a starting point, right? So that will also save us some work. Another good question is, does this actually beat ML approaches? So I think it's hard to say too much about this from the sample size here, but on at least one measure, yes. So back at the beginning of the talk, I was talking about how there are these limitations in modularity and repair in current neural network models. And so at least with regards to that, this technique did hold up to part of the reason I sought out to explore it, which is that I did make individual repairs to individual words during handcrafting, and where I could go in and say, oh, this word is being mishandled. I could go in, fix the meaning of that word, retranslate it, and also have the guarantee that I didn't have other weird side effects for samples that didn't use that word, right? If it didn't use that word, changing that semantics wouldn't affect other parses. And can this work for non-English languages? I've touched on this a few times already, but yes, this can totally work for non-English languages. These categorical grammars have been explored for a whole host of natural languages. One last thing that I just want to touch on briefly is another thing that comes up, and I mentioned this at the beginning, is natural languages have a fair amount of ambiguity. So for the lexicon that I built, here's a table of, for each of the 7 specs, how many different parse trees did we get out, and then how many underlying logical meanings did we get out, right? It's possible to write sentences in basically any natural language such that the sentence could have 2 different meanings. In these cases, we had a wide array of how many parse trees we actually ended up with, but all of them in this case ended up with a single logical form. There's other work that we could build on in the future on probabilistic categorical grammars, in which case you can use probabilities to pick the most likely when there is real semantic ambiguity in a sentence. But then on the off chance that that's not actually what you wanted, we actually can fall back on these derivations that can actually explain which meanings were picked for each word, how the sentence was thought to be put together, and use that as the basis for repair or rewrite, and so on. Thanks.